So pretty much 11.5 is more ways to calculate probabilities. 11.6 is called conditional. So basically it's going to narrow down our polling option because we're setting some condition, this thing happened. And then after that, we really talk about counting. So how to go through and count certain things. What we're going to do right now is talk about or and end problems. That is hot mess. Oh, I didn't mean to zoom in that much. Okay. So we're going to start with or problems. And the idea for this is you're going to have a successful event if this or this criteria happens. So as long as one does, you're good, you're successful. So here we have a successful event. If at least one of the events occurs. Okay. So I'm going to look at an example, and that's going to kind of build our formula that we have. Let's determine the probability of rolling either an even number or a number that greater than 4. On one roll of a die. So as long as I roll an even number, I'm good, I'm successful. If I roll a number greater than 4, I'm also successful. So let's start by listing out, because there's only 6 possible options. What are our successful even numbers? 2, 4, and 6, perfect. And what are our successful numbers greater than 4? 5 and 6, perfect. If I roll any of these, we're good. Okay. So we would be successful if we roll a 2, 4, 5, or 6. Okay. So you see how there's a little bit of overlap between these two? 6 fits into both categories. So one thing that tends to be common is like here, you have a 3 out of 6 chance of getting an even number. 2 out of 6 numbers are greater than 4. So a lot of times what people will do is just directly add them together. So you would think, okay, I have a 5 and 6 chance then that I'm going to complete this event. But really, I've double counted this number. There's not 2 6s, there's a single 6. So I've got to take that into account. Really, I have 4 out of 6 numbers that will be successful. So what is our probability that we will roll an even number or a number greater than 4? How many out of 6? 4 out of 6, perfect. So the probability we roll an even number or a number greater than 4 is 4 out of 6, which you can reduce if you want to 2 over 3. So this is where our formula is going to come into play. If you want the probability of event A or B happening, you indeed look at the probability of each event separately. So probability of A plus the probability of B. 3 out of 6 plus 2 out of 6 gives you 5 out of 6. What you have to do is take into account this overlap. So you subtract the probability of event A and B occurring simultaneously. So this is the main formula we're going to use for OR events. And I'm going to show you with a previous example that this indeed fits in, because it's a lot harder to go through and calculate when you have to list everything, especially if we're dealing with cards, not listing all 52 cards to see overlap of stuff. So from the prior example, fitting it into this formula, the probability that it's even or greater than 4 is equal to the probability the number is even plus the probability it's greater than 4 minus the probability it's even and greater than 4. So this is that number that fit into both categories. You have one number that's even and greater than 4. So that is the number 6. So combining this formula, the probability it's even is 3 out of 6 numbers. 2 out of 6 are greater than 4. And 1 out of 6 is even and greater than 4. So if you add up those numerators, this should be 2 out of 6. If you add up those numerators, 3 plus 2 is 5, minus 1, you get the 4 out of 6 that we were able to see. Make sense so far? Okay. So let's try this with some playing cards, because we definitely cannot do the same thing to list the successful stuff for each event. And then we'll talk about these end problems. We are told one card is selected from a deck of playing cards. We want to determine the probability of selecting first a jack or a spade. Okay. So we've got a couple things that we have to find. We consider each event separately. So what is our probability of getting a jack? How many cards out of 52? Tell you how many there is. Yeah, 4 cards out of 52 are jacks. What's our probability of getting a spade? Where's the 4 go? So there, I don't want to say it without giving it away. It'll be on the bottom, actually. So spades is one of the suits. How many suits are there? You've got spades, clubs, hearts, and diamonds. So there's going to be 4 suits. So your chance of getting a spade is 1 out of 4, because 1 suit out of the 4. Or really, there's 13 out of 52 cards that are spades. So you have 13 of each suit. Does that make sense? Okay, cool. Now we want to look at this final one, this end. What is the probability we get a jack and a spade? So how many cards fit this criteria? There is one card that is a jack and a spade. So you have a 1 out of 52 chance to catch that. So I can't just add these together because I've got a jack that is a spade. It gets double counted. So our probability of getting a jack or a spade is we take the probability of each event individually and add them together. So the probability of jack plus the probability of a spade, and we subtract the probability of getting a jack and a spade. Okay. So much easier than listing out every single card and figuring out, okay, let's count how many are jacks or spades. Okay. So we found all of these. The probability of a jack is 4 out of 52. Probability of a spade is 13 out of 52. And there's a 1 in 52 chance you get a jack and a spade. So you really just add along the numerator. That's 4 plus 13 minus 1 over 52, which is 16 out of 52. And if you want to condense, you can. Top and bottom are both divisible by 4. So the simplest form is a 4 in 13 chance. But if you didn't simplify, that's okay. Does this make sense so far? Let's try a second one of these. Let's determine the probability of selecting a club or a red card. So what is our probability we get a club? (13 out of 52), perfect. What is our probability of getting a red card? How many colors are there in our deck? 2. You can get a red card or a black card. So you have a 1/2 chance of getting a red. Or you can think of it, there's 13 diamonds, 13 hearts. So that is 26 out of 52 cards. So 13 hearts plus 13 diamonds. That is a terrible diamond. Now, what is our probability of getting a card that is a club and it's red? How many cards fit that criteria? If there is a card that fits this criteria. So this card has to be a club and it has to be red. But what color are clubs? Yeah, there's 0 cards. So this is a 0% chance. Clubs are black, so no card is a club and is red. So when that happens, that's great. But now we can go into our probability of getting a club or a red card. It's our probability of getting a club plus our probability of getting a red card minus the probability of getting a club or a red and a red card. So this is 13 out of 52 plus 26 out of 52 minus 0. And it's not sharing. You can't see any of what I just did. There we go. So if we add those together, that's going to be 39 out of 52. I believe so. Which you can simplify if you want to simplify. You can use a calculator to do it for you. 3/4. Feeling okay on these so far? Okay. When this happens, it's impossible for both events to occur simultaneously. We have another way to kind of classify that. So they were completely separate from each other. We call them mutually exclusive. You can't have both simultaneously. So two events are mutually exclusive what is going on here? If it is impossible for both events to occur simultaneously. So ultimately, if you look at the probability of event A and B, it will always equal 0 for exclusive events. And that makes our calculating the probability of A or B much easier. You just add the probability of each event because there is 0 overlap. Okay. All right. So now we're going to try end problems, which we've seen kind of partially in here. Oh yeah, of course. So ultimately, kind of like this example, these events, I can't have a card that's a club and a red card. So I have a 0% chance. Being a club and being a red are mutually exclusive. I can't do both at the same time. So ultimately, this probability in our formula for the OR, when you subtract A and B, this disappears completely because there's no way that both occur at the same time. Unlike our first example, you can have a card that's a jack and a spade. So it just makes the formula for OR a little bit easier. I just add the separate probabilities together. So ultimately, you're still going to go through, you're still going to apply this same formula here. It's just this will disappear completely. So it saves us a tiny bit of work. Yeah, anytime. All right. So we are going to briefly start end problems. And this is mostly going to be not like I need this and this to happen. Instead, what I want is I'm going to do two things. I'm going to do this first event and then I'm going to do the second. And I want to see what's the probability of that. Like rolling the die twice in a row. I'm doing this and then I'm doing this. What's my probability? I get a 1 and then a 5. That's what we want to figure out when we need end problems. So here, to be successful in an end problem, both events have to occur. So to calculate the probability, we have the following. If I want the probability of event A and then event B occurring, I take the probability event A occurs and I'm going to multiply it by the probability event B occurs. So I could sit there, I could make a tree diagram if I want to go through everything, but that's going to be a lot more work than is actually necessary because I can just take these events on their own. So basically, this is your first pick, kind of like our marbles. If I wanted to do the probability, they're both pink. Take the probability of the first one being pink, multiply it by the probability of the second one is pink. Okay. So as just kind of a note, B is that second event. So we assume event A has occurred. That's not, that always looks, never think there's two R's in occurred, but I think there is. But we assume event A has occurred when calculating the probability of event B. So let's try some examples. See what we mean by this. Two cards are selected. With replacement from a deck of cards. We want to determine the probability that two hearts are selected. Okay. All right. So basically, I'm going to draw a card at first, look at it, put it back in the deck. And I want to make sure I'm getting a heart both times. So our first draw, what's our probability of getting this heart 1? So sorry, that's a little confusing. Not the 1 of hearts, just a first heart. So heart number 1. So how many cards out of 52? Yeah, we have 13 out of 52. So you have a 1 in 4 chance on that first draw of getting a heart. Now, I've assumed I've picked my heart because I've got to be successful in both of these events. So that card goes back in the deck. So for our second draw, what's our probability of getting a second heart? 13 as well. You can select all 13 hearts again. So you still have a 1 in 4 chance on that second draw of getting another heart. So my probability that I get a heart followed by another heart is just the product of these two. So the probability of selecting a heart and then another heart with replacement is the following. The probability of getting a heart and another heart is equal to the probability we get a heart on the first one multiplied by the probability we get a heart on the second draw. So I'm going to use that simplified form. That's 1 over 14 times 1 over 4, or 1 over 4 times 1 over 4. You have a 1 in 16 chance of getting 2 hearts in a row. If you tried to set up a tree diagram for this, it would be gigantic. You have 52 events for your first, or 52 possibilities for your first event, 52 possibilities for your second event. You multiply them, you have like 250, no, like 500 and some. I don't even know what 52 times 52 is. It's gigantic. Just kidding. 2,700 possible combinations of cards. So you definitely don't want to sit there and try to draw the tree diagram for that. So this turns out to be a little bit easier. Does this make sense so far? Okay. I'm going to change this again, one word, with to without. And we're going to see how that changes the probability. And then I have one last definition, and then we'll stop there. We'll do another example for this on Tuesday. But now we're told 2 cards are selected without replacement. From a deck of cards. We want to determine the probability that 2 hearts are selected. Okay. So it's very similar, but that without replacement really is going to affect the second one. Doesn't so much affect the first. So for this first draw, the probability of getting a heart does not change. So heart number 1. You still have a 1 in 4 chance, or 13 out of 52. Okay. So simplify that to 1 over 4. Now, when I go to do the second draw, things have to really change a lot. So I'm not replacing this card. So really, how many hearts do I have left? 12. So I've got 1 less heart, but I also have 1 less card overall. I don't have all 52 because 1 is gone. So what goes in the denominator here? I have 51 cards in total now. So here we have 1 less heart to choose from. And we also have 1 less card. Okay. Because at this point, this card gets removed, or this card is now gone. So it's ultimately changed that second probability a lot. but I still do the same thing to find my probability of getting 2 hearts. I multiply these two together. But does this one make sense for the second probability? Okay, so be careful when it says without replacement, that second one is going to change quite a bit. So the probability of selecting 2 hearts is as follows. The probability of getting a heart, my hearts are getting funkier and funkier, and another heart is the probability of drawing a heart the first time times the probability of drawing a heart the second time. So that is 13 out of 52, or 1/4, multiplied by 12/51. And you can do some simplification if you want. 4 goes into 12 3 times. So you have a 3 in 51 chance. And then this simplifies if you want to, but you don't need to. They're both divisible by 3. So I have one last just terminology that relates to these two. Here, when there was replacement, that second one had nothing to do with the first one. This probability was calculated exactly the same way. So these did not depend on each other. They were independent. But here, to calculate the second draw, because I've removed one, this second probability changed. So this result depended on that first one. So we can classify stuff as dependent and independent events. So we say events A and B are independent events. If the occurrence of either event in no way affects the probability of occurrence of the other event. So ultimately, these are ones with replacement. But in this prior example, the first event affected the probability of the second event. These are called dependent. So these are going to be ones that are without replacement. So what we went over last time was kind of talking about and and or problems, and we started doing the end. What is the probability this happens and this happens? And so there's two possibilities. You could have events that depend on each other. So this way the probabilities kind of alter each other. So once this first event happens, it changes the probability for that second. Or they can be independent. So we saw kind of a difference of with and without replacement. If you replace the thing you've pulled out, it doesn't change the probabilities the second time you draw. But if you don't replace it, now I have less of the item, so my probabilities are altered. So we're going to go through one example left, and we're going to see the difference between those two. So we're going to consider the colored envelopes as shown below. So we got 4 groupings. I will label them. we've got envelopes that are pink, and we have 3 of those. I don't need them to be perfect. 1, 2, 3 envelopes that are pink. Then we have blue envelopes, and we've got 2 of those. Well, that's not pretty. That's better. Okay, then we've got envelopes that are green. We have 1 green envelope, and then we also have 1 purple envelope. Okay, and so in total, we have 1, 2, 3, 4, 5, 6, 7 envelopes that we can possibly choose from. Okay, so here there are 7 envelopes in total. So the first thing we want to do is figure out if 2 envelopes are selected at random, with replacement, we're going to determine the probability that 2 things. First, neither envelopes are pink. Okay, so basically the probability the first one's not pink and the probability that second one's not pink. But this with replacement tells us a lot. I'm basically going to draw an envelope, look at the color, put it back in the bag. So with replacement tells us these are independent events, because everything stays the same for that second draw. Okay. So when we go to get the probability that the first envelope is not pink and the second is not pink, remember we just multiply these 2 probabilities together. So we look at the probability, we get the first being not pink, multiplied by the probability the second is not pink. So great. Okay, sorry about that. All right, so we've got this first draw of the envelope. We want to guarantee we get something that's not pink. So if I get blue, if I get green, or if I get purple, I'm good. So I have a 4 out of my 7 envelope chance of getting something that's not pink. Now I've picked that envelope that's not pink, looked at it, put it back in the bag. So everything is still a possibility. So again, my probability the second time I get something not pink is 4 out of 7. So we multiply those, that gives us a 16 out of 49 chance of picking 2 envelopes in a row that are not pink. If I try to do the opposite and figure out what is the probability that both envelopes are not pink, or both envelopes are pink, again, we do pretty much the exact same thing. So we look at the probability the first is pink and the second is pink. So that's the probability the first is pink multiplied by the probability the second is pink. Okay. And so the possibility our first envelope is pink is we've got 3 out of 7. I've picked that pink envelope, I've looked at it, it's gone back into my pool. My second draw has exactly the same probability. So in total, we have a 9 in 49 chance that both envelopes will be pink. Okay. Now, if I change this wording slightly, so I'm going to cheat. I'm going to duplicate this. So we're still going to calculate the same probability. 2 envelopes are selected from random. without replacement. So now I've in turn created dependent events because once this first one happens, I now only have 6 envelopes that are left in my pool to choose from because I'm not putting anything back. So this creates a dependent event. Okay. The probabilities are still calculated in the same way. If I want the probability neither is pink, the probability of no pink envelopes is equal to the probability the first is not pink times the probability the second is not pink. So same exact setup. First draw is still the same. I have 4 out of 7 envelopes that are not pink. So this first probability is 4 out of 7. For my second draw now, I have a bit of a problem. So going back up here, I've picked one of these envelopes. Doesn't matter which one I've crossed out. I no longer have 7. I've got 6 envelopes to choose from, 3 of which are not pink. So my probability is changing for the second one. I have a 3 out of 6 chance of getting something that is not pink. So without actually looking at it, you can kind of do it right from here. You pulled an envelope, so you have 6 remaining. You used up one of your options. So instead of having 4 non-pink, you have 3. So in the top, you've used 1 non-pink up. And you also have 1 less envelope in your pool. Okay. So ultimately, you can just multiply across. If it says to simplify, though, 3 over 6 is really half. And then you can go ahead and condense this. 2 goes into 4 2 times. So you have a 2 in 7 chance of drawing 2 non-pink envelopes. And then if we do the same other one with replacement or without replacement, if we want both envelopes to be pink, again, that second probability is going to change. So the probability of drawing both pink is equal to the probability the first is pink multiplied by the probability the second is pink. Our probability, again, is still exactly the same. You have a 3 in 7 chance because 3 envelopes are pink out of the 7. So we have a 3 out of 7 chance. And again, for the second probability, I've now used up an envelope. So I only have 6 envelopes in total. I've used one of the pink up. So instead of 3 being left, I have 2. So here, 1 pink envelope is gone. And then we also have 1 less envelope in the pool still. Okay. And then likewise, we can simplify this. 2 over 6 is the same as 1 over 3. So really, the 3's cancel. Now you have a 1 in 7 chance of drawing 2 envelopes that are both pink. So a little better odds. Okay.